In this video, we're going to pull together everything we've learned, looking at stoichiometry, solution stoichiometry, reaction predicting, all of it. Okay, so let's go ahead and see how we pull it together. First up, what happens when aqueous solutions of sodium chloride and potassium carbonate are mixed? Well, let's think about what this means. Let's say I have a solution of sodium chloride. Separately, I have a solution of potassium carbonate. In my sodium chloride solution, that means I have sodium ions and chloride ions floating around. And for every one sodium ion, there is one chloride ion as well. And they're just random in here. Okay, I know I tend to write them grouped just by accident, just because I'm writing by space, but they are randomly in there. For potassium carbonate, for every two potassium ions, I have one carbonate ion. Because again, chloride, NaCl, potassium carbonate, K2CO3. And I'm going to mix these together. I know that sodium chloride is aqueous. Why? Because when it's in solution, when it's in water, they want to dissolve. The ions want to dissolve and be free flowing and flow around the solution. Potassium carbonate, same idea. It's aqueous. But I'm going to mix these two things together. So I'm going to bring these together, and there's not going to be a barrier between them anymore. Now the ions can float around as they want, and they can mix up each other. Okay, wherever they want to go. Now, by predicting rules, we want to try to put the opposite things together. So we say, well, we know cations and cations don't want to go together. And so, like, the potassium ion here and the sodium ion here are not going to want to be together. Cations don't want to be together, and anions don't want to be together. Like, we know that. That's pretty straightforward. But you have to remember your solubility rules to be able to do the rest of this question. So as these are floating around, the sodium ion may come across the potassium ion, but it doesn't care, doesn't want anything to do with it. They're the same charge. They're going to repel each other. A sodium ion may come across that chloride ion, but it had already let the chloride ion go. Why would it come back to it? The sodium ion may come up to a carbonate ion, and you may say, well, it just needs two of them. But again, sodium is a group one metal. It's an alkali metal. Sodium salts are always soluble. So even if the sodium does come up and find that carbonate, it's going to float away. It doesn't want to be there. Same thing with the KCl. It's not going to want the carbonated or get rid of it. It definitely doesn't want the potassium or sodium because it's both positively charged, both cations. But it doesn't want the chloride either. If there's water around, it's going to come across, see that chloride and be like, nah, I'm good. And it's going to keep floating around. So what happens is no reaction. Both predicted products are soluble. Again, you predict it by move this up so I can write underneath it. The cation of one to the anion of the other, cation of one to the anion of the other. And so Na2CO3 is soluble. KCl is soluble. There's no driving force to this reaction. Therefore, there's no reaction. Nothing's going to happen. What about this solution? What happens when aqueous solutions ammonium carbonate and silver acetate are mixed? Same idea. We've got two beakers. In one beaker, we've got ammonium carbonate. Ammonium is NH4 plus. Carbonate is CO3 2 minus. Now, ammonium carbonate I know is soluble because ammonium salts are always soluble. So that means that for every two ammoniums I have in solution, I have a carbonate in solution as well. So for every two ammoniums, I have a carbonate as well. Separately from that, I've got some silver acetate. Acetate salts, always soluble. Silver, always a +1 charge. Acetate, CH3, COO minus, or you can write it as C2H3O2 minus. I have zero preference on that. But for every one silver ion in solution, there is one acetate, also in solution. So for every one silver, there's an acetate. Silver and an acetate, and a silver and an acetate. Okay, so for every one of one, there's one of the other as well. Now I'm going to mix these two together and think about what's going to happen. So I mix these two together. I've got one big solution, and now these ions are going to float around. Silver ions are going to come across, and they're going to see the ammonium, but they don't want to be with ammonium. There's no way. They're both cations. They don't like each other. Silver finds the carbonate, and it's like, oh, wait a minute. This is a good pairing. This is insoluble. Carbonates don't want to be soluble. So that ammonium, or sorry, silver ion finds that carbonate ion, and it's like, oh yeah, we'll hang out. The ammonium goes along and it can find the acetate, but again, it doesn't care. The acetate and the ammonium don't want to pair up. They're always soluble. So these just keep floating around, doing their thing wherever they want to be. But the carbonate floats around and it's like, wait a minute, I just found two silver ions. I'm going to go ahead and pair up. And when they pair up, they make silver carbonate solid. So the driving force of this reaction is the formation of that silver carbonate. So my molecular equation shows NH4, 2, CO3, aqueous, reacting with AgCH3COO, aqueous, to produce, again, cation from one to the anion of the other, NH4, CH3COO, but again, that's aqueous. Those are going to keep floating around in solution. And Ag2CO3, which is solid. I do need to balance this, so I need a 2 in front of here. My net ionic reaction is just one carbonate ion finds two silver ions and makes silver carbonate. So the driving force of this reaction is the formation of ammonium carbonate. But what's going to happen? I'm going to form silver carbonate. I think I keep saying ammonium. I mean silver. I'm forming silver carbonate. That is the driving force of the reaction, and that's what's going to happen. I'm going to form solid silver carbonate. Okay, on this one, I'm not going to draw the picture, but I recommend you try it yourself. Okay, I think it can help you guys really see what's happening in solution. But what happens when aqueous solutions of copper 2 sulfate and ammonium sulfide are mixed? Well, what's copper 2? Copper 2 means copper 2 plus. Sulfate is SO4 2 minus. So I've got CuSO4. Sulfates are usually soluble. This is not an exception to that. The sulfate is soluble. This is going to produce, or this reacts with ammonium sulfide, so NH4 plus and S2 minus. So, oh, sorry, that is aqueous. I have two ammoniums, two NH4 pluses to every one sulfide, S2 minus. Sulfides are usually insoluble, but ammonium salts are always soluble, so this is an exception to that rule. In these, when I swap partners, I'm going to form copper sulfide and ammonium sulfate. So copper sulfide is insoluble. Again, most sulfides are insoluble, and this is not an exception to that. And then ammonium sulfate, which is soluble, because ammonium salt's always soluble. So that one is soluble. But the driving force of this reaction is the formation of the copper 2 sulfide. So if I wanted, again, this is your molecular equation, but if I wanted your net ionic, which just shows the driving force of the reaction, I have a copper 2 plus ion reacting with a sulfide ion, forming copper 2 sulfide. And that is the driving force of your reaction. That's why it's even proceeding. What's up next? Some math. When 1.25 liters of a 0.0500 molar lead-2 nitrate solution and 2 liters of 0.0250 molar sodium sulfate solution are mixed, calculate the mass of precipitate that is formed. Okay, first it's telling me precipitate form, so I know something's happening. I know a reaction is happening here. So let's go ahead and write out a reaction. We've got lead-2 nitrate. Lead-2 nitrate is PbNO3 2. Nitrate salts are always soluble. This is reacting with sodium sulfate, sodium Na2, sulfate SO4. I need 2 sodiums for every 1 sulfate because of charge. Sodium salt's always soluble. Swap those partners. I'm going to form lead sulfate, which is insoluble, and 2 moles of sodium nitrate when it's balanced out, which is soluble because sodium salts are always soluble and nitrate salts are always soluble. I should know my solubility rules for sulfate anyway, but if I didn't, the fact that I know sodium nitrate has to be soluble, and I know this has to form a product, kind of clues me in as well that the lead-2 sulfate is my insoluble product. Write down what you're told. Let's see, you've got 1.25 mil or liters of a 0.0500 molar solution here, and you have 0.0250 molar 2 liters here. Remember what this information tells you. This information can get you to moles. This information can get you to moles. So I have moles and moles, which means I have a limiting reactant example. One's limiting, one's in excess. I don't know which is which. So let's figure it out. I'm going to solve this one by determining how many milliliters of the sodium sulfate I need to completely react all of my lead-2 nitrate. Or sorry, how many liters? We have liters in this question, so I'm going to use liters. So I'm going to figure out how many liters do I need? I don't know yet, but we can figure it out. And I'm doing this because it will help me determine what my limiting reactant is. If how many milliliters I need is less than I have, then I know what my limiting reactant is. If it's more than I have, I still know what my limiting reactant is. Either way, I'll figure it out. So number of liters of Na2SO4. I've got a 0.05 molar solution of lead-2 nitrate. So 0.0500 moles PbNO32 for every 1 liter of solution. And notice I'm intentionally writing the lead-2 nitrate solution there. I'm doing that for the simple fact that I want to make sure I'm using the right solution at all points. I have 1.25 liters of that solution. So this step right here cancels out my liters and gives me my moles of my lead-2 nitrate. Now I can use that balanced reaction, which is 1-to-1. I see that there is 1 mole of sodium sulfate consumed for every 1 mole of lead-2 nitrate consumed. This cancels out my moles of lead-2 nitrate and gets me into moles of sodium sulfate. So now I can use that molarity as a conversion factor. I know 1 liter of sodium sulfate contains 0.0250 moles of sodium sulfate. Calculate this out, and I get an answer here of 2.50 liters of Na2SO4. So that means in order to react all of my lead-2 nitrate, I need 2.5 milliliters of the sodium sulfate, but I don't have that much. So this very quickly tells me that this is my limiting reactant and this is my excess reactant. Now I can answer the question. I know I only have 2 liters of sodium sulfate, therefore sodium sulfate has to be my limiting reactant. Therefore, I'm going to go ahead and solve this question using that as the math for my limiting reactant. How many grams of lead 2 sulfate can I make? I've got a 0.0250 molar solution of sodium sulfate, which is 0.0250 moles of sodium sulfate to over 1 liter of sodium sulfate solution. In total, I have 2 liters of this solution though. I see from a balanced reaction that 1 mole of PbSl4 is produced for every 1 mole of Na2SO4 consumed. And my mass of lead 2 sulfate, I add that up. Lead is pretty big. Lead's like 207.9 or something like that. It's pretty big. Sulfur is 32.07, 4 options at 16 grams each. 303.3 grams PbSl4 for every 1 mole of PbSl4. Again, lead is a really big atom. This gives me 15.2 grams of my lead 2 sulfate. Check my sig figs, 3 sig figs everywhere. Yep, I've got 3 sig figs, so 3 sig figs is my final answer. So 15.2 grams of lead 2 sulfate. How many liters of a zero point 0.1 molar HCl solution are required to completely react with 13 grams of magnesium carbonate? Okay, to do this question, first thing I'm going to do is figure out what the reaction is. I have to know what's reacting. I have to be able to predict what the products are so I can even answer the question because I need a balanced reaction. So I know I've got HCl reacting, and I know hydrochloric acid is a strong acid, so AQ, and it's reacting with magnesium carbonate. Magnesium is Mg2 plus, carbonate is CO32 minus, so 1 magnesium to 1 carbonate, and that is a solid. But again, they can react because the HCl will dissolve the magnesium carbonate. When I look at this, I immediately think double displacement reaction because I've got cation, anion of each side. So I'm going to swap my cations and my anions. This gives me magnesium chloride, which is aqueous, and carbonic acid, which is also aqueous. But I need to recognize that this will decompose to form a gas. This is a double displacement reaction that results in a gas production. So my actual products here are magnesium chloride, water, and CO2, or carbon dioxide gas. I do need to balance this reaction, and I notice I need 2 chlorides and and 2 hydrogens on the other side, so I need a 2 in front of the HCl, and now it is balanced. So again, this portion in the middle didn't really, this happens, but very, very quickly. So my actual products are here. But now I have my reaction, I've got it balanced, I can go ahead and do the problem. So I want to know liters of HCl. So number of liters of HCl, I am reacting 13 grams of magnesium carbonate. So 13.0 grams, convert that to moles. That weighs 84.32 grams for every mole. Now that I'm in moles, I can use my balanced reaction, and I see that 2 moles of HCl react with every 1 mole of magnesium carbonate. Now I've got moles of HCl, so I can use that molarity to find the number of liters of HCl. So every 1 liter of HCl I have contains 0.11 moles of HCl. It's always a good thing, just check, make sure units are canceling, grams to grams of magnesium carbonate, moles to mole of magnesium carbonate, moles to moles of HCl, and I'm left with liters of HCl. Calculate this out, and I get an answer of 3.08 liters of HCl. Let's check our sig figs just to make sure. 3 sig figs, 4 sig figs, exact, and 3 sig figs. So my final answer does in fact need 3 sig figs, and we are good to go. In order to react 13 grams of magnesium carbonate with a zero point 0.1 molar HCl solution, it will take 3.08 liters of HCl. So if you really need to neutralize magnesium carbonate, I recognize using a stronger solution so you don't have to use 3 liters of it because that's going to create a lot of waste. Okay. Potassium sulfite is mixed with sulfuric acid. Determine the overall molecular equation and net ionic equation for this system. Potassium carbonate, or sorry, potassium sulfate. Got carbonate in my mind now. Potassium is K plus sulfite, SO3 2 minus. So K2CO3. I need 2 potassiums for every 1 sulfite. All potassium salts are soluble. This reacts with sulfuric acid, H2SO4. Again, if you forget sulfuric acid, remember ic acid came from 8. So sulfate is SO4 2 minus. I give it enough protons to make it neutral, hence H2SO4. These react, and you're going to swap partners here. Cation from one to anion of the other, cation from one to anion of the other. So I'm going to form K2SO4. I still need 2 potassiums for every 1 sulfate just to charge balance it. But then I form H2SO3. I need to recognize this is sulfurous acid, and sulfurous acid is one of the ones that breaks down into a gas evolution. So it is a double displacement to gas evolution reaction. So my actual products here will be the K2SO4 as described, and the H2SO3 decomposes to form water, and the remainder is a gas. The remainder is SO2 in this case. So that's my molecular equation. My net ionic is showing the driving force of the reaction. What basically you're pulling out and ignoring the spectators. My spectators here, spectators are the potassium and sulfate. So everything else, because everything else is included in something that's not aqueous. My hydrogen is being putting into the water, my sulfur and my oxygen here into the sulfur dioxide. So my net ionic, SO3 2 minus, aqueous, plus H2. Sorry, that is not H2. That is 2H plus because sulfuric acid is 2 protons and a sulfate. It is an ionic compound. So 2H plus here, giving me H2O liquid and SO2 gas. This is your net ionic. Calculate the mass of solid sodium chloride that must be added to 1.50 liters of a 0.1 molar silver nitrate solution to precipitate all of the silver ions in the form of silver chloride. Okay, so I've got sodium chloride, and I want to know how much I need to add to a solution. If it goes into a solution, it's going to be aqueous. It may be solid up front, but it will dissolve when it's put into water. It's going to react with silver nitrate, which is also aqueous. When I swap partners here, I'm going to get sodium nitrate, which is still soluble, and silver chloride, which is insoluble. And the question itself helps identify that as well, because it does say all of the silver ions in the form of silver chloride, emphasizing that they will be precipitated out. I want to know the mass of sodium chloride needed to do this. I have a 0.1 molar solution of silver nitrate. and I have 1.5 liters of that solution. At this conversion, all I have left is my moles of silver nitrate. So now I can use my balanced equation. You should check that it's balanced. I just knew this one was balanced. I knew everything was +1 or -1, but I always check to make sure it's balanced. It is in fact balanced. So I see that 1 mole of NaCl reacts with every 1 mole of silver nitrate. Again, even though mathematically it appears that this step isn't doing anything, you must include it if you want credit for your work. It's showing me you understand your conversions. Now I've got moles of sodium chloride, because again, check your units here. Your liters of silver nitrate have canceled. Your moles of silver nitrate have canceled. Your moles of sodium chloride. Multiply that by the mass of sodium chloride, 58.44 grams of NaCl for every 1 mole of NaCl. And you get 8.77 grams of NaCl. Check your sig figs. 3 sig figs, 3 sig figs, exact, and 4 sig figs. So we are good with 3 sig figs. It will take 8.77 grams of sodium chloride to precipitate all of the silver ions out of the solution in the form of silver chloride. What happens when aqueous solutions of barium nitrate and potassium sulfate are mixed? Well, barium's group 2, so it's +2 charge. Nitrate, -1. Potassium group 1, +1 charge. Sulfate, -2. So I've got barium nitrate reacting with potassium sulfate. And I'm going to swap those partners and see what happens. Barium to sulfate, potassium to nitrate. Barium sulfate is one of the cases where sulfate is not soluble, so that is going to form an insoluble salt. And then KNO3, aqueous, balance that out. If you want this is your molecular equation. Your net ionic would remove those spectators. So you have barium 2+ ion reacting with sulfate ion. Forming your barium sulfate. What's next? Sulfuric acid dissolves aluminum metal. Suppose you want to dissolve an aluminum block with a mass of 23.4 grams. What volume of 18.4 molar of sulfuric acid would you need? Density is 1.8 grams per centimeter cubed. Okay. I've got sulfuric acid, H2SO4. Strong acid, acids are aqueous. Dissolving aluminum metal. Aluminum is a solid. They're going to swap here. This is going to be a single displacement reaction. The cation is going to replace cation. So it's like where we say metal replaces metal, but in this case, it's not a metal replacing, it's cation. The aluminum is going to replace the hydrogen ions. So I'm going to form Al2, SO43, which will be aqueous, and then hydrogen gas. We do have to balance this out. I need 3 sulfates on each side. I need 6 hydrogens on each side, and I need 2 aluminums on each side. Now that I've got a balanced reaction, how much sulfuric acid do I need? So I'm going to go with mils. Again, because it doesn't specify, you could technically stop at liters and no one could say anything, but I like mils better. It reinforces conversions, plus we're most likely going to measure to mils anyway. We have 23.4 grams of the aluminum. One mole of aluminum weighs 26.98 grams. I'm in moles of aluminum, so I look at my reaction and I see that I have 3 moles of sulfuric acid consumed for every 2 moles of aluminum consumed. Now I'm in moles of sulfuric. Now I can use my molarity as a conversion factor. I've got 1 liter of H2SO4 for every 18.4 moles of sulfuric. This gives me my liters of sulfuric. Convert to milliliters. And I see I need 70.7 milliliters of my 18.4 molar solution. Check to make sure your conversions are right. Grams of aluminum, moles of aluminum, moles of aluminum, moles of sulfuric, moles of sulfuric. This is the volume of whatever you're dealing with, but here we've got sulfuric. Liters of sulfuric, you get moles of sulfuric. It did give me the density in the question. Why? Useless information for this question. We don't need the density here. I just need 70.7 mils of that 18.4 molar sulfuric to dissolve 23.4 grams of an aluminum block. What's next? How many grams of silver chloride can be formed when 25 mils of a 1 molar silver nitrate solution is mixed with 30 mils of a 0.75 molar magnesium chloride solution? Let's write out that reaction. So I'm mixing silver nitrate, AgNO3, which I know is aqueous, with magnesium chloride, MgCl2, which is also aqueous. I'm going to swap those partners. So I'm going to form silver chloride, which is insoluble, and magnesium nitrate, which is soluble. I'm going to go ahead and balance that reaction. So a 2 here and a 2 here will do that for me. I'm then going to look at the question and say, what information do I have? I am told that I have a 1 molar solution of of silver nitrate, and I have 25 mils of that 1 molar solution. And I have a 0.75 molar solution of magnesium chloride, and I have 30 mils of that solution. Hopefully this helps you recognize that you have a limiting reactant question, because we have enough information to find the moles of each species. Now, I have no idea which one is it. We're going to have to figure that out. I'm going to do it just by chance, solving the number of mils I need of magnesium chloride. How many mils of magnesium chloride do I need to react all of my silver nitrate? I have a 1 molar solution of silver nitrate, so 1.00 moles of AgNO3, so 1 liter of the AgNO3 solution. And I have 25 mils of the AgNO3 solution. Sorry, 25 mils needs to be in liters, 0.0250 liters of the silver nitrate solution. This gets me in moles of silver nitrate, so now I can use my balanced equation, and I see that 1 mole of magnesium chloride is reacted for every 2 moles of silver nitrate reacted. This gets me into moles of magnesium chloride. Now I can go ahead and use my molarity. I know that for every 1 liter of magnesium chloride solution I have 0.750 moles of magnesium chloride. I'm gonna go ahead and just convert this to milliliters right now, because that's what my values are in. I have 1,000 mils of magnesium chloride for every 1 liter of magnesium chloride. Again, I don't care if you don't show this specific step as long as you do it correctly. This tells me I need 16.7 mils of that magnesium chloride solution. So I asked myself, do I have enough? I have 30.4 mils. I need 16.7 mils. I have enough. That means that my silver nitrate is my limiting reactant and my magnesium chloride is my access reactant. But that means I will use the silver nitrate concentration and volume to determine how much silver chloride I can make, because that's going to control the number of grams of my target product, which is the aluminum, which is the silver chloride. So number of grams of AgCl, number of grams of silver chloride produced. I have 1 mole of silver nitrate, or 1 liter of that silver nitrate solution. I have 25 mils of it, so 0.0250 of the silver nitrate. Looking at my balanced reaction, I have 2 moles of silver chloride being produced for every 2 moles of silver nitrate consumed. Again, mathematically, it's going to cancel each other out, but I have to show my conversions. And silver chloride weighs 143.35 grams for every 1 mole of silver chloride. And I don't have this one written out, so 1 second while I calculate it. I get 3.58 grams of silver chloride. Check to make sure I have my sig figs right. I have 3 sig figs here, 3 sig figs here. This is exact, and I actually wrote down 5 sig figs here, so 3 sig figs here. 3.58 grams of silver chloride is how much I can make based on this reaction and based on these conditions. What's up next? Sulfuric acid can be neutralized with potassium hydroxide. It requires 22.3 milliliters of a solution of potassium hydroxide to completely react with 42.7 mils of a 0.125 molar sulfuric acid solution. What is the concentration of potassium hydroxide solution? Okay. Potassium hydroxide is KOH. It is one of my strong bases. It is soluble. Potassium hydroxide reacts with sulfuric acid, which is H2SO4. Also one of my strong acids. Or sorry, it's a strong acid. So strong base plus strong acid is a neutralization reaction. But neutralization still swaps partners. So I'm going to form K2SO4 and water. You form salt and water. Now, balancing this out, I'm going to form 2 moles of water, and I'm going to need a 2 here. So again, it's kind of hard for students to see that swapping at first. The swap of this one is pretty easy, but H2 plus OH, well, the form when you mix those things together, you're not going to make peroxide. You're going to make water. Acid plus base always gives you salt plus water. You just happen to need 2 moles of water being formed to balance out your reaction. So I've got my balanced reaction. Now I can go ahead and do what I need. I'm trying to find the molarity of that KOH solution. So I want the number of moles of KOH over the liters of KOH solution. I know my sulfuric acid solution is 0.125 molar. So 0.125 moles of H2SO4 for every 1 liter of H2SO4. And I'm told I used 42.7 mils, which is 0.0427 liters of the H2SO4 solution. At this step, I'm in the moles of sulfuric. So I'm going to use my balanced equation, and I see I get 2 moles of potassium hydroxide reacting with every 1 mole of sulfuric acid. I have my moles of KOH. Now I need that over volume to get it over liters of KOH. I used 22.3 milliliters, which is the same as 0.0223 liters of KOH. And this gives me 0.479 moles of KOH over every 1 liter of KOH solution, which you can also write as just 0.479 molar KOH. Again, always check your sig figs. Usually it's 3, but not always. 3 sig figs, 3 sig figs, exact. 3 sig figs, so 3 sig figs. Okay, what's next? What volume of a 0.150 molar potassium chloride solution is required to completely react with 0.150 liters of 0.175 molar lead 2 nitrate? Let's write out that reaction. I've got potassium chloride, so KCl, reacting with lead 2 nitrate, PbNO3 2. Swap those partners. I'm going to form potassium nitrate and PbCl2. PbCl2 is insoluble. Need to balance this out, so I need 2 nitrates, 2 potassiums, 2 chlorides. I want to find the volume, so number of milliliters of KCl. I have a 175 molar solution, so 0.175 moles of lead 2 nitrate for every 1 liter of the lead 2 nitrate solution. I have 0.150 liters of that lead 2 nitrate solution. So that gets me to moles of lead 2 nitrate. Now I can use that balanced reaction. 2 moles of KCl are consumed for every 1 mole of PbNO3 consumed. I've got moles. I don't want moles, I want volume. I know it's a 0.15 molar solution, so 1 liter of KCl solution contains 0.150 moles of KCl. And then 1,000 mils of the KCl solution in 1 liter of the KCl solution. This gives me 350 mils of KCl is required. Let's talk about sig figs really quick. We've got 3 sig figs, 3 sig figs, exact, 3 sig figs, exact. So I need 3 sig figs here, and that's why I have the decimal place right there. The decimal place makes sure that 0 stays held up and is one of your significant figures. Solid magnesium reacts with hydrochloric acid to form an aqueous solution of magnesium chloride and hydrogen gas. How many mils of a 0.899 molar hydrochloric acid solution are required to completely react with 1.92 grams magnesium metal? Yeah. So I've got magnesium metal reacting with HCl. This is a single displacement where the metal won't replace the metal, but the cation replaces the cation. So I'm going to form magnesium chloride and H2 gas. Balance this out. I need to know the number of mils of HCl. I'm starting with that 1.92 grams of magnesium. One mole of magnesium weighs 24.31 grams. So in my balanced reaction, I see that 2 moles of HCl react with 1 mole of magnesium. Now I'm in moles of HCl, so now I can use that concentration of hydrochloric acid I have right here. I see that 1 liter of HCl solution contains 0.899 moles of that HCl solution. And just because I like things in milliliters, 1,000 mils of the HCl solution. For every 1 liter of the HCl solution, 176 milliliters of HCl. Check your sig figs, 3 sig figs, 4 sig figs, exact conversion, 3 sig figs, exact conversion. Both 3 sig figs in my final answer. It will take 176 milliliters of HCl to completely react that magnesium metal if the concentration is 0.899 moles. What about this? Write the net ionic equations for the following reactions. Sodium metal reacts with water, hydrobromic acid reacts with ammonia, and silver nitrate reacts with copper metal. Okay, so sodium metal with water. That is a base. Sorry, that is a metal reacting with water. Sodium metal, Na solid, is going to react with water. And when this reacts, it's going to form sodium hydroxide, which is aqueous, and hydrogen gas. It's a single displacement. We'll talk about the net ionic in just a sec. But notice the cation is replaced, the metal is replacing the cation in the system. So I'm forming sodium hydroxide and water and hydrogen gas. What I have to recognize is that I want net ionic here, and this is a strong base, meaning it splits apart in water. So my true net ionic here, Na solid, 2 moles of H2O, we're going to balance this out in a minute. You're going to need a 2 in front of here, a 2 in front of here, and a 2 in front of here to actually balance this out. That's where these numbers are coming from. But so 2 sodium, 2 waters, just going to form that H2 gas, but then your net ionic tells me I formed 2 moles of sodium ions and 2 moles of hydroxide ion. So it is a single displacement reaction. Notice in this one, there's no spectators, everything's involved. Let's talk about hydrobromic acid with ammonia. Hydrobromic acid is a base. Or sorry, I'm saying that I'm writing in one spot and I'm reading another, which is not happening, which is not helping. Hydrobromic acid is an acid, ammonia is a base. Acids plus bases react to make salt plus water. In this case, hydrobromic acid, HBr, reacts with ammonia, and this is going to form, it's going to be a synthesis reaction. It's going to combine and form NH4Br. Okay. Now, I did say acids and bases make salt plus water, and they do. That's when it's a strong acid, strong base. It's not always the case when it's a weak acid, or acid with a weak base, or vice versa. So you got to be careful with that idea. Okay. This is a again what we call a synthesis reaction. And everything's going to combine. But this is soluble. And so this is where the trick to this question comes into play. What I have to recognize is the bromide is really a spectator the whole time. I have H plus ions that are donated to the ammonia to allow it to form ammonium. So the ammonia is acting as the base and picking up that proton from that acid that's readily giving it away. The bromide here is just a spectator. And last but not least, I have silver nitrate reacting with copper metal. So silver nitrate is a salt, copper metal is, well, a metal. So let's think about what's happening here. I have silver nitrate. I know that's soluble, reacting with copper solid. That copper is going to displace that silver, forming copper, most likely copper 2 nitrate, truthfully. Copper 1 nitrate is not as common. And silver solid. And if I balance this out, I get a 2 there and a 2 there. This is a single displacement reaction. One metal has displaced the other. What's my spectator? Or what's my net ionic here? 2 moles of silver ion reacted with 1 mole of copper solid, forming 1 mole of copper ion and 2 moles a silver solid. Notice here, it's your nitrate that is the spectator. So here, no spectators. Here, my spectator is bromide. And here, my spectator is the nitrate. What volume of a 0.100 molar barium hydroxide solution is required to completely neutralize 25 mils of a 0.125 molar nitric acid solution? Well, let's think about your reaction here. You got barium hydroxide, strong base, so soluble, and it's reacting with nitric acid, strong acid, completely soluble. Swap those partners. You're going to get barium nitrate, still soluble, soluble salt, and water. Balance this out. You're going to need a 2 here, and you're going to need a 2 here to balance it out. So I want to know, I have a 0.1 molar solution here, but I don't know the volume to neutralize a 0.125 molar solution here and 25 mils of it. So this is what I'm trying to find. Number of mils of barium hydroxide. I'm starting off with 0.125 molar HNO3. So 0.125 moles of HNO3 to 0.12 to every liter of that solution times 0.0250 liters of the HNO3 solution. Now I'm into moles of HNO3, and I can convert to moles of barium hydroxide. 1 mole barium hydroxide reacts for every 2 moles of nitric acid consumed. And my moles of barium hydroxide, so I'm going to use that molarity. I know 1 liter of the barium hydroxide solution contains 0.1 moles of barium hydroxide. And again, just because I prefer things in milliliters, 1,000 mils of that barium hydroxide solution for every 1 liter of barium hydroxide. And this gives me 15.6 milliliters of the barium hydroxide. Check your sig figs, 3 sig figs, 3 sig figs, exact, 3 sig figs, exact, 3 sig figs. So it will take 15.6 milliliters of a 0.1 molar barium hydroxide solution to completely neutralize 25 milliliters of a 0.125 molar nitric acid solution. Doesn't take as much because the barium hydroxide has twice as much hydroxide in it as the nitrate does. And so for every 1 barium hydroxide neutralized, 2 nitric acids are neutralized. So that's why it takes a little bit less. And our last example. Bone was dissolved in hydrochloric acid, giving 50 ml solution containing calcium chloride. To precipitate the calcium ion from the resulting solution, an excess of potassium oxalate was added. The precipitate of calcium oxalate weighed 1.437 grams. What is the molarity of the calcium chloride in the solution? Okay, so let's think your way through this. You've got some solution that you put a bone in, and you got 50 mils of it. Okay, that's a calcium chloride solution. For every 1 calcium, there's 2 chlorides. So the bone was dissolved in HCl and it made this. So basically, the calcium from the bone is in the solution and it reacted with that chloride and it dissolved it. Cool. To this, I'm going to add an excess potassium oxalate. So I'm going to add some K pluses and some oxalate. The calcium and the oxalate like each other so much that when they find each other, they pair up and they precipitate out as calcium oxalate. And that's where it says the precipitate calcium oxalate. So I add enough of the K2C2O4 to react all of the calcium ions in solution. And this, I isolate from that 1.437 grams of calcium oxalate. So that means I can assume that all of the calcium oxalate in here came from that original calcium chloride solution. I've got CaCl2, which I know is aqueous, reacting with K2C2O4, also aqueous, forming KCl and CaC2O4. What I want to know is how many moles of CaCl2 do I have per liter of solution? I know I have 1.437 grams of the calcium oxalate. Convert that to moles. 1 mole of calcium oxalate is 128.1 grams. Now I'm in moles of calcium oxalate, so now I can convert to moles of calcium chloride from the balanced reaction. So 1-to-1 ratio. But again, you need to show this conversion if you want full credit for your work. That would get me the moles of calcium chloride, but I want a molarity. So I divide this by the volume of that solution, which was 50 mils, so 0.0500 liters of the CaCl2 solution. And this gives me a concentration of 0.224 molar calcium chloride. Check your sig figs. You have 4 sig figs here, 4 sig figs here. It's exact here, but only 3 sig figs here. So my final answer can only have 3 sig figs as well. So 0.224 molar calcium chloride is our molarity of that solution.